Alright, so in this video we're going to talk about mathematical induction, and that's basically just a way to prove formulas, and they usually have to do with series, and I kind of gave up on trying to write on this thing, so I'm just going to type it. So for the first example, we're going to prove that 2 to the 0 plus 2 to the first plus 2 to the second all the way through to plus 2 to the n minus 1 is equal to 2 to the n minus 1. And so n is going to represent the number of terms in the series. So if n equals 2, then it's just going to be the first two terms, which is 2 to the 0 plus 2 to the first. And so when you have a number of terms, you don't want to have to add them all up, because if you have like 1,000 terms, then you're not going to want to add up 1,000 numbers. So these formulas are really helpful to try to reduce it down to a easy way to represent it. So the first step is always going to be to prove it for n equals 1, because it really doesn't make sense to try to prove something if you can't even prove it for the first term. And also it's important to prove for n minus 1 for reasons that we'll talk about later in the video. So if we plug in 1 for n, then we're going to get 2 to the 0, because it's only one term. So you just take the first term of that series, and then you set that equal to 2 to the first minus 1, because we're plugging in a 1 for n and we had 2 to the n minus 1. And so then you can just work that out to get 1 equals 1, and that is a true statement. So we did prove that it is true for n equals 1. So now we're going to assume that it's true for n equals k, where k is just any number. And that might not seem like it makes sense to do right now, but later you'll see why that's really important to this process. So you plug in a k anywhere you see an n in the above series, and you just get 2 to the 0 plus 2 to the first plus 2 to the second all the way through 2 to the k minus 1 is equal to 2 to the k minus 1. So now with that information that we assume that it's true for n equals k, we're going to prove that it's true for n equals k plus 1. So we're going to take what we already assumed in the last one, and we're going to try to work from there. So since we want to prove that this is true for n equals k plus 1, we're going to want to add another term to the series. And so you can't just add it into the series without adding something to the other side. So we're going to add 2 to the k to both sides. So you can see that that will give you 2 to the 0 plus 2 to the first plus 2 to the second all the way through 2 to the k minus 1 plus 2 to the k. And then that's going to be equal to 2 to the k plus 2 to the k minus 1. And then you can use your exponent rules to rewrite that as 2 times 2 to the k, because there's 2 of them. And then that's 2 to the first times 2 to the k minus 1. And then you can rewrite that as 2 to the k plus 1, because when you multiply two powers, you add them. And so the final result is 2 to the 0 plus 2 to the first plus 2 to the second, all the way through 2 to the k minus 1 plus 2 to the k is equal to 2 to the k plus 1 minus 1. So now you should be able to see that the result we got there, just by manipulating the equation that we assumed was true, is the same as if we would have plugged in n equals k plus 1 to that equation. So if we would have plugged in n equals k plus 1, then we would have had 2 to the k plus 1 minus 1, which is the same as 2 to the k. And on the other side, we would have had 2 to the k plus 1, which is what we have. So now the last step is going to be our goal, which is to prove that it's true for all n, which means any integer you plug in for n, it's always going to be true. So any number of terms, it's always going to work. So what we basically just proved in the last two steps is that if it's true for k, which we don't know that it's true for k because all we did was assume that it's true, but if it is true for k, then it definitely has to be true for k plus 1 as well, because in step 3 we moved around the equation for n equals k, and we showed that it's the same thing as the equation for n equals k plus 1. So that means that if it's true for k, then it has to be true for k plus 1. So now we know that there's a relationship between k and k plus 1, so we can set up a chart And in the first step, we prove that it's true for 1. So we're going to put k equals 1. And we know that that works because we already showed that. And then if it works for 1, then it has to work for 1 plus 1, which is 2. So that's a result of what we just proved at the beginning of step 4, which is if it's true for k, then it has to be true for k plus 1. So if it's true for 1, then it also has to be true for 1 plus 1, which is 2. And now that we have that it's true for 2, we also know that it has to be true for 2 plus 1, which is 3. So now you can see that this chain is going to go all the way down through infinity. So we started with 1, which we knew was true because we proved it. And then we also proved that if it's true for 1, then it has to be true for 1 plus 1, which is 2. And then if it's true for 2, it has to be true for 2 plus 1. And if it's true for 3, it has to be true for 3 plus 1, which is 4. And then 4, it will be true for 5. And so that's going to go all the way down. You can add 1 to every number, and it's going to go all the way down through infinity. And so, in Mr. Glennon's words, it is thus proven.